right. Hi, everyone. Welcome to Research on the Road.
Okay, good. All right, how's it going, everybody? Wildman Dan here, or Daniel Quinones. Just want to say thank you guys so much for joining us today. We got a very special presentation. We're going to be going over whales or cetaceans, correct? Somebody correct me if I'm wrong.
Yep, correct.
Thank God. I still remember from marine biology. Now, I'm more of a herpetologist, which you guys know already. I love my reptiles, but I have always had a fascination with world's biggest mammal. I absolutely love whales. I'm fascinated by them, and my biggest desire in this world is to get in the water with one of them, and hopefully I'll be able to do that. But let's turn it over to Michael real quick. He's going to talk about some of the past history of cetaceans and whales, and we're going to get a good look at what they used to look like back in the day. I'm assuming how big they used to be, and maybe some other bits of information that we just didn't know. Michael, go ahead and take it over, man.
Thanks, Daniel. So whales, they're known today as the majestic, gentle giants of the sea. Well, I guess they're only gentle unless, like, if you're not krill or fish or something that it eats. But to us, they're gentle giants, fortunately. But they weren't always these big krill-eating behemoths as we know them today. They actually have pretty humble beginnings, and we're going to explore that today. And so this presentation is called Walking with Whales. Now, why on earth, if I'm talking about whales, why am I talking about walking? They don't walk, they swim. Everyone knows that. And that's true, but that wasn't always the case. In fact, whales evolved from these terrestrial ancestors that lived completely on the land, like other mammals. But first, today we have two main groups of whales living today. There are the mysticetes, the baleen whales. Those are the really big ones, like blue whales, humpback whales, fin whales, etc. And then they are toothless and instead have this kind of shaggy-looking, what's called baleen, hanging down, which they use to filter feed krill. And this baleen is made of keratin, which is the same material that makes up of our hair and our fingernails and stuff like that. But they do not have any teeth, unlike the odontocetes, or the toothed whales. And if you've ever seen a dolphin or an orca, you know that they have a toothy smile that they use to prey on fish, seals, kind of whatever they want. Now, you might have also heard the factoid, or I want to say it's a factoid. You might have heard the claim, I sure have, that killer whales aren't actually whales. They're actually giant dolphins. And that's half true. So it's true that killer whales are pretty closely related to dolphins, and they really are big dolphins. But dolphins are just as much whales as these mysticetes, these baleen whales that we're so familiar with. But there's a third group that you might not have heard of unless you're really into paleontology, and those are the archaeocetes, or the ancient whales. And they are all unfortunately extinct, but we're going to go over them today and how they developed into the forms we know today. So if you've never seen the skeleton of a whale before, here's a brief primer, because they are weird, probably a lot weirder than you would expect. So this is a skeleton of a baleen whale. I believe this is a bowhead whale, and you can see where it gets the name bowhead whale from the big arching bow-shaped skull. And so in life, it would have baleen kind of hanging down here to catch little fish and krill and so forth. But they are very strange looking animals. I mean, just look how much of the body the head takes up, and how strangely the mandibles and rostrum is shaped. And then way back here, you have these weird little bones that aren't even connected to anything. What could those be? Well, you might have guessed those are actually the remnants of the whale's pelvis. Not all whales have these, but some of them do. It kind of just varies depending on what species you're looking at. But they have these remnant, or what's called vestigial, legs. And they're obviously not walking around on these today, but as the further we go back, the more we realize that it wasn't always this disproportionate. Moving on to other whale skeletons, this is a skeleton of a toothed whale, specifically a sperm whale, and you can see it's just this big concave thing. It looks like it has a big dent on its face. And I included a photo of kind of the skull with the other soft tissue, just to give you an idea of how this, why its skull is shaped like this, right? And it's shaped like this because it has to incorporate the melon, which is an echolocating sense organ, as well as some muscle and fatty tissues and stuff in the front of its face. And all toothed whales will have this kind of concave shape on their face because they have to incorporate what's called a melon, which is used for echolocation. Now, whales are not the only type of mammal to eventually migrate into being aquatic. It's happened at least 4 or 5 other times in mammals, including the sirenians, also known as the manatees, dugongs, and sea cows, the seals, sea lions, and walruses, sea otters, and river otters, and these extinct group of animals called desmostylians. Now, desmostylians are pretty cool. They were these big, heavy-set hippo-like animals, but they weren't hippos. They were actually more closely related to elephants, but they were very much their own unique thing. And their fossils can be found right here in Southern California. They actually have really, really unique molar teeth. But what's interesting about especially the manatees and dugongs is that just like whales, we can trace very well their ancestry from land to water. And so there is an animal called Pesosiren, which literally looks like a manatee with legs. It has the same wide set body and the same skull, except it has 4 legs instead of these flippers. So whales are one of the first to make this move to the water, but not the only ones. So when we're looking at whale ancestors, our journey begins back in the Eocene epoch, about 50 million years ago. Now, this was not too long after the extinction of the dinosaurs. And so dinosaurs dominated the earth for such a long time. And so you have all of these ecological niches just completely open. The earth is barren of any large animals. And so basically what we see is mammals stepping up to the occasion and taking the place. And we see mammal diversification just explodes during this time. And whales are no exception. But we're going to start our journey with Indohyus. Now, when you look at this, your first thoughts are not whale. I would be shocked if it was. And this thing indeed is very, very, very different from the whale today. But Indohyus was about a cat-sized artiodactyl. Artiodactyls are the even-toed hooved animals. That includes deer and antelope and pigs today. And this animal, Indohyus, probably resembled and acted a lot like a chevrotain or mouse deer today, which is this cute little bugger here. Probably would have acted a lot like Indohyus did. Spent some time in water. And we know it spent a lot of time in water because its bones were what we call osteosclerotic, or their bones were very dense, basically, which is good for having ballast and balance in the water. But we can tell by oxygen or carbon isotope ratios in its bones, we can tell what it ate. And we know that it was not eating things that lived in the water. It was eating land animals and land plants. This animal is very unique because if it wasn't, so up till now, we can basically say like, oh, it's just like a small cat-sized deer pig thing. Pretty cool, pretty cute, but nothing too special. Except this animal has what's called an involucrum. Now, an involucrum is a special thickened ear bone that up till this discovery has exclusively been found in whales. But here it is, this cute little cat-sized deer thing having a specialized bone that's found in whales. What was it doing with that? Well, we'll see in a bit what it could lead to. And an important point is that this is not a direct ancestor to modern whales. But it's probably a close cousin and closely resembled the true ancestor of whales. Now, I mentioned the term artiodactyls on the last slide, and I want to explain what those are. So artiodactyls are the even-toed hooved animals, and those include cows, deer, pigs, sheep, antelope, giraffes, and animals like that. So you're very familiar with artiodactyls, even if you don't know the word. And a genetic study in the 80s or 90s, I think the 1990s, revealed that whales are actually genetically most closely related, and actually fall within the group Artiodactyla. And those results might be confusing at first because you're like, they live in water. They're giant. They don't look anything like a deer or a sheep or a goat. But that's what the genetics revealed. And this was actually later confirmed by the fossil record by animals such as Indohyus. And the closest modern relative of whales is none other than the humble, gentle hippo. Actually, they're not gentle at all. Hippo is actually quite terrifying. But another unique feature of artiodactyls is a bone called the astragalus. Now, the astragalus is found in most vertebrates, and it's just one of the ankle bones, basically. But the ankle bones of artiodactyls, of these even-toed animals, have what's known as a double pulley system, where you have kind of two grooves on both the top and bottom of this ankle bone. And so I outlined in blue the ancestors of whales here. So Indohyus, that we talked about on a couple slides ago, you can see has 1, 2, 3, 4, the double pulley system. Pachycetus, which we will address shortly, also has this double pulley system, as do pigs and deer and giraffes and sheep and so forth. As opposed to the ankle bone of, say, dogs, which all other mammals will have just one here, just one projection here, as opposed to a double pulley system. So Pachycetus. Pachycetus was about the size of a dog, but it was actually an amphibious whale. And it's typically regarded as the earliest known whale that we can definitively say, like, this is where whales got their start. This is where they first split off from the non-whale ancestors. So the whales and hippos would have shared a common ancestor, and once they split up, this guy was the first in line to be a whale. Their nostrils were on the very tip of their snout, kind of like we see in crocodiles today. And again, we can tell from the carbon isotopes in its bones that it ate freshwater fish and small mammals. So it was not feeding on marine life as opposed to its ancestors. And paleontologists debate exactly how much time this animal spent in water, because just like Indohyus, it has osteosclerotic bones, or the dense bones, which are good for weighing yourself down in water. And as you can see in the skull or the skeleton, its eyes are sitting close to the top of its head, just like a crocodile, which is good for if you're standing in the water or swimming in the water, and you still want to be able to be submerged, but see out of the surface. And so it has a mix of traits that say that it was spending a lot of time both inland and in water. Now, Amblyocetus, the full scientific name of this animal is important because it's Amblyocetus natans, and that literally means walking, swimming whale. Natans specifically means swimming. Ambulos means water, or walking or waddling, and cetus is whale. So you have the walking whale that swims. And just like the name suggests, it did walk, it swam, but it wasn't really proficient at either one. It had its limbs sprawl out to the side, kind of like a crocodile. And so it was very, very awkward and ambling on land. And in the water, it wasn't swimming around like a modern whale. It was just kind of probably punting along the bottom of a river. But this animal was an ambush predator, so it would have lied in wait, waiting for an animal to come take a drink of water, and then lunge and try to drag it underneath. Its nose, just like Pachycetus, was towards the tip of the snout. And we can tell from oxygen isotopes in its bones that this animal lived in brackish water. So that's kind of a mix between freshwater and saltwater. So it would have lived in estuaries and deltas where rivers were flowing into oceans. And you might think, you might look at the skull and think that looks kind of familiar. And you might hear me say it's an ambush predator that lied in wait in the water, waiting to drag animals to their doom. And if this sounds familiar, it's because we think that these animals would have acted a lot like modern day crocodiles, acting as ambush predators. And so you can think of these early walking whales as sort of like mammalian crocodiles, and they would have acted pretty similarly. Moving on down the line, we have my favorite group of walking whales, which are the Remingtonocetids. They're my favorite for no other reason than they are just so darn cute. They have very, very long, skinny skulls. And we have, we can tell in the skulls where the most nerve endings were. So sometimes there are large holes where nerves and blood vessels would have ran through. And there are a concentration of those holes called foraminifera towards the tip of the snout, which suggests that they would have had lots of whiskers and bristles in that area. Their vision was not fantastic, which suggests that they didn't really need it, probably relying a lot on these whiskers to feel around, kind of like animals living in caves do, or catfish. So this animal could have been spending time in some murky water. But whatever the conditions of the environment it was living, we know it was a fully marine animal. This animal, Remingtonocetids, also had a decreased inner ear, which the inner ear is important for balance in land animals, and this animal was slowly losing that function. And so we can tell that this animal is fully aquatic because on land, it would be pretty discombobulated. And so because of the inner ear decreasing in size in Remingtonocetids, scientists think this group kind of represented the point of no return in whales. So this is where they were on the trajectory of becoming fully aquatic, and at this point, there is no turning back. Myocetus is a very interesting example. Myocetus was another early whale whose pelvis was not fully connected to the spinal column, which is, so it wasn't fully detached like we see in modern whales, but it was getting there. So it wouldn't have been a proficient walker on land. It was spending most of its time in the water. However, we actually have a fossilized fetus of this animal. We have a pregnant mother, and the fetus here is this purple bones, and this is a skull. And you can see the skull is pointed towards the back of this animal. Now, why is that significant? Well, fully marine animals today, like whales, the young are born tail first, because if it was born head first, that's, several minutes where it has to hold its breath, otherwise it would drown. So when it's born tail first, that gives it the most time to hold its breath to get up to the surface for its first breath of fresh air. And because this animal is being born head first, we can infer that it was probably giving birth on land, just like modern day otters and seals. So we can infer some of the lifestyle habits of this animal because we happen to have a pregnant female, which is, I cannot stress enough how incredibly rare that is to find a pregnant animal in the fossil record. We're continuing on the trajectory of whales becoming fully aquatic with Dorudon. Dorudon was probably the first of the whales that actually looked like whales. Had very reduced hind limbs, and so this thing was not walking on land whatsoever. These limbs are not supporting its weight. It was 100% aquatic. And even though at first glance it looked a lot like modern whales, it has the tail fluke here, has the flippers in the head, and everything looks basically right. When you look at the skull of this animal, it's pretty gnarly. They had very different teeth than modern whales do, especially modern baleen or toothed whales. You can see these teeth are very jagged and triangular shaped. And towards the front of the mouth, it had the more uniform conical teeth that we see in most whales today. But this tooth is actually why the original name for this group of animals was the Zeuglodons, or the yoke teeth, because paleontologists thought these teeth they thought they looked like the yokes that you put on oxen. Next up, we have Basilosaurus, and this was the first big whale. And when I mean big, these things were very, very big, up to 60 feet long or more. And so these things exceeded or rivaled at least the length of the giant mosasaurs from the Cretaceous period that are now extinct at this time. We have the teeth have a lot of wear on them, which suggests that these animals actually chewed their food before swallowing instead of swallowing it whole or tearing it into chunks. These animals were actually like mashing on bone and flesh. What's really unique about Basilosaurus is if you ever see the skeleton of a Basilosaurus in a museum, so this is Basilosaurus, you can see very long, very serpentine, unlike modern whales, which are very kind of barrel chested. These things are very skinny. But back here we have, again, like we saw in the baleen whale earlier in the presentation, we have very tiny hind limbs. And modern whales have hind limbs that are like, there's like 2 or 3 bones in them. They're really incomplete. But Basilosaurus still has 100% complete hind limbs. All the bones are here. You have the pelvis and the femur, not the radius and ulna, the tibia and fibula, ankle bones, toes, and even a kneecap. But so despite this thing definitely not using its legs for walking, it still had not completely lost its legs yet. Continuing down the line, getting closer to the present day, we have an animal called Achiocetus. And this was a very special animal because it had hard teeth, like we see in Odontocetes today, but they were pretty widely spaced out. They weren't packed together like you would expect. And so paleontologists have reason to believe that there would have been baleen in between these teeth. And so it would have had both teeth and baleen. And so this animal suggests that whales developed baleen while they were losing their teeth. So their teeth were becoming widely spaced out, baleen came in, and eventually they just lost their teeth altogether, and the baleen took its place. But that's not a for sure thing. That's only one theory, because we also have Maya baelina. Maya baelina is an entirely toothless whale, and it was a suction feeder, kind of like a lot of whales today, where they will suck in and they'll create a vacuum underwater, and it'll just suck any poor fish or krill or whatever prey it was eating into its mouth to swallow. And so the discoverers of this individual, you can see it's totally toothless, no teeth, no baleen, nothing. And so the discoverers believe that this fossil suggests whales that developed baleen after they completely lost their teeth. And so that's kind of contradictory to what this fossil suggests. And that's not saying that we can throw everything out. It just means that we need to study these animals a little more closely. We need to nail down the time spans maybe, or we just need to discover more animals. So I remember when Maya baelina was actually presented at a conference for the first time. I think that was 2018 or 2019. But the authors before this presentation were talking about, oh, well, we have 4 possible origins for baleen whales. And we don't know exactly which one of these this is, but we have this nailed down, but we don't have any toothless whales. So it has to be one of these 4 options. And then these guys got up right after that and were like, well, it's funny that you say you don't have any toothless whales, because now we do. And so those types of really interesting interactions can happen at conferences all the time. But that just complicates this issue of what came first, the baleen or the teeth, or did they phase out, or did one disappear before the other? We just don't know yet. And that's what's exciting about paleontology, is because we're making new discoveries all the time. But speaking of baleen whales, this is a fetus of a fin whale that's unfortunately dead. But when we discovered that baleen whales actually develop the tooth buds in utero while they're developing as a fetus in the mother, they develop these teeth buds for a short amount of time. And so tooth buds are the very beginning stages of tooth development. And they never develop enamel. They never actually erupt from the gum line like our teeth do. But they still have these tooth buds that form and then are eventually absorbed later in development. Further, we've known for a while that baleen whales actually have the genes for teeth in their genomes. Now, they're inactive. They're not going to grow teeth anytime soon, but they still have the genes for them, which is really, really interesting. And sure enough, we find genetic evidence first, usually, and then often we'll find fossil evidence and what's called morphological evidence, physical evidence, that confirms those observations from the genome. Now, a question that you probably have is why did whales move into the water? We don't know for sure, but there's a few hypotheses why. So my personal hypothesis is that there was so this was shortly after the massive Cretaceous extinction. And in the Cretaceous and Jurassic, there were these enormous marine reptiles like ichthyosaurs, plesiosaurs, mosasaurs, pliosaurs, these giant reptilian sea monsters dominating the water. Now, all of a sudden, they're totally gone, and the ocean is absent of any large predators, except sharks, I guess. But even the sharks weren't ginormous during this time. And so these early whales essentially seized the opportunity. The oceans were ripe for the picking, and so they kind of just dove on in, so to speak, and took over those niches and quickly grew to very large sizes. At the same time, you could have had other land predators kind of outcompeting these early whales and pushing them more and more into the water. And so it could be a combination of both or something else. And it's also worth mentioning during this time, the oceans themselves were undergoing major physical restructuring. So the continents, like we saw at the very beginning, the continents were mostly, or they're getting pretty close to their modern day places, but they're still kind of settling in. The sea levels were higher, and so we have seaways opening and closing. And so these would have presented a lot of new environments for these whales to move into. And actually, I'm going to go all the way back to the beginning to show you the paleo map of, oh, there we go. There we are. So this was the Earth, what the Earth looked like when the whales were first evolving. And we can see all of these oceans kind of indicating Europe and Asia, which is where a lot of the early whales are found right about here. And Indo-Hyas, which we talked about first, was found about here. So they're right on the coasts of these inland seas. And, you know, slowly but surely, they evolved into the whales as we know them today. And so that went on pretty long. I could literally talk all day about this stuff. This is a very, very hyper-condensed version. But that will do for now, and I will turn things over to Emily.
So whale, what have we here? Just a basic overview of whales. So going into more of the present situation and the future of the whale populations. So whales are cetaceans, as Daniel so brilliantly remembered. They are warm-blooded mammals that give birth to live young, nurse their young, and have hair, even though it's not much beyond infancy. And as Michael touched on, or actually went into detail on, is Odontoceti versus Mysticeti are the branches of our cetaceans. And so we looked at the skeletal structure of them in that Mysticeti roughly translates to mustached whales, and they have the baleen plates, and those are the filter feeders. So our baleen whales, our largest whales, are the ones that are filter feeding some of the smallest organisms in the ocean, plankton and krill, and very small organisms that they are ingesting. Whereas our Odontoceti might be smaller whales, but they are the toothed whales and actually eat larger prey. So Michael said dolphins are part of the toothed whales. So we've got within the dolphins and porpoises, we've got the Delphinidae branch, which is the one that includes the oceanic dolphins. So bottlenose dolphins and orcas are similarly toothed whales. It's one of those things where you're just subcategorizing and splitting hairs to the point where yes, an orca is a dolphin, but both of them are whales. So here's what we saw with Michael, our toothed whale versus our baleen whale, just the general skull structure. So in our cetacea, here I was saying we have our Delphinidae, our oceanic dolphins, our porpoises, our river dolphins, There's 4 species of river dolphins, which often go overlooked when we're talking about dolphins that do live entirely in fresh water. But I want to look a little bit more specifically at the Mysticeti subbranch that is the rorquals, which are the blue whale, humpback whale, fin whale, and sei whale. So the very largest of the whales, the very largest animals to have existed on Earth, are the rorquals. And so this naming for them, the rorquals, refers to these furrows that they have along their chin, and they're very obvious when you see them feeding. So there's a total of 10 species. We listed a few of them there. They are the largest of the baleen whales, and this is where their rorqual name comes from. You see those fringes when they expand their jaw. It expands and balloons outwards, and those folds that are in their chin allows it to balloon outwards and to stretch and expand so that they can take the largest intake of a gulp of water so that they get the maximum number of plankton and tiny organisms to filter out, because they are huge animals that eat very tiny food. So they have to eat a lot in one bite. And so along our coastline, our western coast of North America, this is sort of the breakdown of where these oceans are, or where these whales are in the oceans. And there are whales in every ocean in the world, Arctic, Antarctic, regardless. There are, if you are in an ocean, there is a very small chance that you will see a whale, if you're lucky. The thing is, they have seasonal migration patterns. Most whales have some form of migration pattern, and that includes the dolphins. It varies a lot more among the dolphins, but as far as the baleen whales go, it's typically a hemispheric thing. So if you divide the Earth at the equator, you have the groups that go from the Arctic down to the equator, and those that go from the equator down to the Antarctic. So there's not a lot of overlap there. They're not traveling from pole to pole, but they have groups that travel from pole to equator in whichever hemisphere they choose to live in. So here's where our humpback whales are typically migrating. So the blue dots are where they're feeding, and the pink is where they are breeding. So you can see the polar regions are very rich in nutrients and plankton and krill. And so that's where they're going to feed. They're going to spend their summers there. They're going to eat as much as they possibly can. And then they're going to travel along those routes to where the pink dots are and spend their winters in the nice tropical warm waters at the equator. So for the extent of this, I really want to focus on whale communication. That's something that we can't see in the fossil record. So it's something that's extremely important to all whales. And so the Mysticetes, the baleen whales, they're more low in the frequency of sound. So it's more of like a bass pulsing that you would hear from them. Like gray whale sounds, it's more of like a knock or a burst or bout, and there are patterns to these that the whales are able to recognize, and it does differ, and there's different types of calls among them. So sound travels farther and faster through water than it does in the air, about 4.5 times faster, and that's important for these big, deep voiced whales like the blue whales that produce these low pulses and groans and moans that are oftentimes below what we would even be able to hear. If they were playing it on a speaker, it would not be something you can hear without manipulation. It's so low on the sound frequency. But that's very important because those low frequency waves, those low energy waves, travel a lot farther. So the sound tends to get reduced as it loses energy, but the wider the peaks in our wavelength of sound, the farther it can go before it dissipates. So these blue whales don't cross paths with each other very often. They're huge animals, they're solitary animals, and they have to communicate over entire ocean basins. So if they use these low frequencies, they're more likely to be able to hear each other's calls even from great distances. So here's an overview of what we talk about when we're talking about frequencies and high and low sound. So our baleen whales up there at the top, their range goes way down below the below human hearing and even below what seismic surveys and sonar and that sort of thing is emitting into the ocean. So it's well below what we think of as sound. But it is a very low continuous vibration. As we move forward, as we move to higher frequencies, we're going more to chirps and loud calls, not necessarily loud, just higher frequency calls. We're looking more at, so the dolphins, they've got that cackling little chirp, and porpoises and those sorts of things. You can imagine that's a high frequency sound. And as we go higher and higher and higher in the frequencies, then we get outside of our range of hearing as well. So we're in a narrow spectrum of this chart on what we are able to actually hear. So the whales can produce sounds that we can't hear because they're too low, but the dolphins and porpoises, they can produce sounds that are too high for us to hear. And that's where we're talking about echolocation. So back to the baleen whales for a moment, we'll talk about whale songs. And that when you think of whale communication, that's the go-to, that's what everyone thinks of first. And there aren't that many species of whales that can actually do that. And the one that we associate whale song with is humpback whales. Blue whales, fin whales, bowheads, and minkies can to some extent produce what we would consider songs, but it's not that characteristic whale song that we know from humpback whales. And here's our beautiful humpback whales. We don't know why they sing though. Obviously it's for some sort of communication, but why do they need to have this pattern of communication, and what is it telling the other whales? So we do know that only males sing. So that's a hint. That's a good step in understanding. But maybe it's to show off to the ladies. Maybe they're trying to attract females. Or maybe they are trying to deter other males from coming in. Maybe they're marking their territory and saying, anyone within hearing range, this is my area, go find your own. It could also be for orientation purposes. That's one of the hypotheses. However, if it were for orientation purposes for migration, it wouldn't necessarily be restricted to only the males. You would expect to see it in males and females across the species. So whale songs are really interesting topics of research and ongoing research because we don't know why they sing. We also don't really understand what they're singing and how it's working, because it's not just that these different species have different songs, but different groups within that species have different songs. So there's accents depending on where your humpback whale population is. If you're talking about your humpback whales in Hawaii, they're singing different songs than those that are in other parts of the world. So our humpback whales have accents and dialects that they change based on the group that they're talking to, but then also year by year. It's really interesting that there's an actual seasonal change to the way these patterns are going. So researchers might study the whales for a year, think that they've got a recognizable pattern that they've detected among the whales, the way they're communicating to each other, and then come back the next year and find that it doesn't follow that pattern anymore, that they've changed the way that they're speaking. They have new words that they're telling each other. And beyond that, they can sing for hours and hours and hours, repeating the same song, or they can switch it up and change it around. So the message that is coming across is still a work in progress. We would love to understand it, but we're far from it. The toothed whales, so our dolphins and sperm whales, they don't have that very low frequency. They're more social. They tend to be in groups, so they don't need to have that sound carry across the entire ocean. Their communication is more direct. They're with each other most of the time. And so they have higher frequencies, and beyond that, they use echolocation. So even their calls to each other, even their direct communication is higher frequency. But if they go even further in that high frequency, then we're talking about echolocation. And that's where Michael mentioned the melon. That bulb at the front of the forehead is actually being used to focus these sounds that they're creating. And they have what's called phonic lips up in their skull, up in their forehead, that are manipulated, and air is forced through them, kind of like our lips would be. So we can change what we are saying based on how we move our lips. They change what they're saying and the sounds they're making based on these phonic lips. And they're up in the top of the forehead instead of down at the bottom of where their mouth is. But that's because that's where the sounds are coming from, being focused through that melon and out, and then the sounds bounce back to them, and they are detected by the auditory bulbs in the brain, and then that signal can pass through and be recognized as basically an image. They can understand what is around them, what's in their surroundings. Is that object moving? How big is it? What speed is it moving, if it is? And what direction is it moving? So here we talk about sound is so intrinsic to the way that all of these whale species live. It's vital to the way that their social groups work. And so it might be difficult to discern certain sounds if you're relying on sounds for communication underwater, because there's ocean sound, just natural ocean sound from breaking waves constantly, rain, lightning strikes. If you're in polar regions, there's cracking sea ice. There's undersea volcanoes and earthquakes, and there's these amazing species called pistol shrimp that can snap their claws at so loud that they actually create a bubble that is hotter than the surface of the sun. So that we'll come back to on another live stream, because I love pistol shrimp. The problem here is where man-made sources are starting to muddle things. So our shipping routes, the seismic devices that we use, and sonars that all ships use, and especially military ships use, are really posing a threat to whale communication and the way that these species live. So there's several ways that we think they're impacted with it. It could change their behavior. You can imagine just constant noise is stressful as a background sound. It's especially stressful if you can't hear what you're hoping to hear. If you can't hear the call that you're expecting from a family member or a distant species or anything like that. So, and this is primarily shipping pathways, because those shipping is going on 24/7, and all of these ships not only have noisy engines, but they're using sonar so that they can guide themselves through the water, and it's really created a lot of background noise that is inescapable in any ocean. We think it can also cause hearing loss in some of these animals. The way that they perceive sound and the way that sound works in their auditory system, it could be affected by these frequencies that we are emitting through sonars. And the reason that this is so problematic is because we often see strandings of whales and dolphins, where a stranding being where they come up on shore, or they land themselves, beach themselves, and they can die from dehydration because they really do need to be submerged in water, or they can be crushed by their own weight because these are very large animals and they need that water for buoyancy to support their bulk. And as time goes on, we're accumulating more and more evidence that naval exercises using active sonar, and that's important, active sonar. There is a difference in the way that we use sonars and like background and like everyday shipping versus these naval exercises. We have found a lot of evidence that this active sonar coincides with mass strandings. And so environmentalists have asked the Navy to limit sonar and explosions in areas where marine mammals are known to be at certain times of the year. So we have a pretty good understanding of where whales and dolphins tend to be, where they accumulate for their migration routes. And if we can pay attention to that and we can limit the effects that we are having on that area, we have an obligation to do so. So here's just one paper that I picked, and this is referring to beaked whales. So beaked whales are toothed whales. They resemble dolphins, but they're not in the dolphin family. They are very odd animals that we don't know that much about. We do know that there's about 23 species of them, and I say about because they live so deep down and we see them so rarely that we don't know that much about them. There might be fewer species and we're just seeing diversity within a smaller subset, or maybe there's a lot more species that we just haven't encountered. And so they are among the deepest diving mammals in existence. They go extremely deep and stay there for a very long time. They also seem to be disproportionately affected by this active sonar, because most of the time when we see them, it's when they've stranded themselves. And so that this type of sonar that seems to affect them so much was only introduced in the 60s, and there's been at least 12 mass strandings of beaked whales since then that have been near definitively tied to it. And then 27 other mass strandings are near a naval base or ship and are likely associated with it. So there's definite concern there. And here's a few of our beaked whales. So this is Cuvier's beaked whale. They're fairly large, but they look like dolphins, right? And here's Blainville's beaked whale, so just another type. If you didn't have the scale there, you might just think that they look kind of like a porpoise or a bottlenose dolphin, but they are in a separate group from them. They just resemble them. And so takeaway from that is we really need to be aware of the impact that we're having on the ocean, and not, I mean, the obvious pollution and contamination and just overexploitation of the ocean. But beyond that, we even have to think about things like sound pollution, because there's so much that we don't know about what's going on in the water, and there's so much that we are doing to impact it without knowing the effects that it has. So that's the end of my discussion.
Well, thank you so much, Emily. And before we say goodbye, I just thank you so much to all of our viewers and everybody watching right here. Don't forget, you can find us also on Facebook and also our YouTube channel, as well as Wildman Dan. Make sure you take a look at us. We have a lot of content on there that we would love for you guys to see, share, like, and don't forget to follow us. Thank you guys also once again. We want to say goodbye, and thank you for joining us once again. Thanks.